This video is going to be spin in Bohmian mechanics, and so it's going to be about how Bohmian mechanics or pilot wave theory can handle the phenomenon of spin. And so spin is definitely one of those things that when I first learned about Bohmian mechanics, I was thinking, how can Bohmian mechanics account for spin? But this paper, which is also by Travis Norson, is going to show how Bohmian mechanics can account for spin. And I was going to try and do the rest of the paper in this video as well, but it was already getting quite long. So this one will be about spin. The next one will cover more things about the contextuality of spin and entanglement and things like that. And so this is only going to be on the first part of this paper. And so as I have been saying throughout these videos on Bohmian mechanics, what pilot wave theory says that it can recapitulate the predictions of textbook quantum theory using just the Schrodinger equation and the guiding equation, which tells us about the velocity of the particle, the speed and direction that the particle is moving in response to the wave function or the guiding wave. And so, like I said, in the last video, I covered this paper here, which was about scattering and quantum tunneling. This one is going to be the first part of this one on spin. And so also, as I have been sort of repeating, is that being able to recapitulate these predictions from textbook quantum theory is a necessary but not sufficient condition for a candidate interpretation of quantum mechanics to be plausible. So as I've been saying, the textbook quantum theory is extremely successful on being able to make accurate predictions. And so if your candidate theory of quantum mechanics, your interpretation of quantum mechanics can't explain those, or it gives wrong predictions, then it's not going to be a good candidate for an interpretation of quantum mechanics. And so what that means, though, is that neither of these papers offer any new or deep insight into reality, but they simply just want to demonstrate how pilot wave theory can give the same predictions for these phenomena as textbook quantum mechanics. And so, as I said, this video is covering the first part of this paper here, and it has to do with spin. And so, when talking about spin in quantum mechanics, we are often talking about the Stern-Gerlach experiment. And so this is looking at a non-uniform magnetic field here. We shoot our particles through it. In the original Stern-Gerlach experiment, they used silver ions. And so then when they enter this magnetic field, they will get separated based on the spin. It's completely probabilistic. So you can have, say, 50% of them going up and 50% going down, and we get these peaks on here, where in classical expectation, if we were thinking about these as having spin in, any sort of angle away from completely up and down, we would get a nice uniform detection on our screen here. But we only see these two peaks here, telling us that when after it goes through this non-uniform magnetic field, that this then becomes either completely spin up or completely spin down. And if you then took just the spin up ones and sent them through another Stern-Gerlach device, but say it was rotated into and out of the screen by 90 degrees, you would then get 50% spin up in the x direction and spin up or spin down in the x direction. And so then if you took just the ones that were spin up in the x direction and sent them through another Stern-Gerlach device that looks like this in the z direction, you would again get the 50-50 chance of going to spin up or spin down. And so what that tells us, or at least in the standard quantum mechanics interpretation, it's saying that these are non-commutative, so they are not compatible properties. And so when you do the experiment in the x direction, you essentially just erase any sort of memory of ever having done that first one in the z direction. And so, like I said, the Bohmian mechanics is going to have to try and recapitulate this prediction using just the Schrodinger equation and the guiding equation here. So again, what's written in these lecture notes down below is copied almost verbatim from part of this paper, but I have made some alterations and exclusions and additions for clarity. All right, so I have some of this highlighted in red, and that's what I'm going to focus on here. And so this first part here is just describing the Stern-Gerlach experiment. And so we want to do something like in figure 1 by imagining a magnetic field that's very strong but non-zero and only a vanishingly small region. And so this is the figure from the paper here where we want just a very almost delta function like magnetic field here. And so we have our wave coming in that has this width in the z direction, that's w, and so it's going to have a length. So this is the figure that I made from the previous video. So it's going to have a length of L here. And so this is going to go through here, and what we see is that the wave is going to split like this, so we have this overlap region here. And so just like in the previous video, it's in this overlap region that the sort of interesting things are happening. And so this description here, so a neutral spin half particles with initial spin state, so in this superposition of up and down here, move in the y direction toward the Stern-Gerlach apparatus with magnetic field gradient along the z direction, so the magnetic field is going in the z direction here. The field delivers an impulse in the plus or minus z direction to our particle spin here, components of the beam. So downstream there arise two spatially non-overlapping sub-beams with amplitude of this c sub plus and c sub minus, so that is these two beams right here. In ordinary quantum mechanics, a measurement of the position of the particle downstream of the Stern-Gerlach device will find the particle in, or more accurately, cause it to materialize in the upper/lower beam with a probability of the c squared here. All right, so going down here, so again, this is just telling us the Hamiltonian that we're going to get for this. We can imagine a plane wave packet like those described in the previous paper, which I talked about in my last video. The initial wave function should be a packet of length L, as I said, in the y direction. So we have this L in the y direction here, and width W along the z direction with constant amplitude in the region where its amplitude doesn't vanish. Propagating initially in the plus y direction with reasonably sharp defined energy. Let us again start by assuming that the incident particle spin degrees of freedom are described by the eigenspinors here. And so what this means, again, with the constant amplitude is that outside these very small trailing and leading edges here, the amplitude stays exactly the same throughout the length of this wave packet here, so that for most of it, we can think about it as a plane wave. So that's why he calls it, in scare quotes here, a plane wave packet. All right, so then in the time period during which the incident packet is interacting with the field, so with the magnetic field at y equals 0, so remember we have the magnetic field as almost a delta function right here at y equals 0. The wave function can be taken to be up to an overall time-dependent phase, which we omit for simplicity, to be this. So this is our wave function here. So again, we can kind of see that we have kind of an incident wave, a reflected wave, and a transmitted wave. And so this is in the appropriate regions of the YZ plane. And so this part here in black is just telling us about sort of the continuity of our wave function at that sort of delta function magnetic field. So far, we have assumed that the spin degrees of freedom are given by one of the z direction eigenspinors, but now we appeal to the linearity of the Schrodinger equation in order to write a solution appropriate for an arbitrary initial spinor like this one right here. So then we get this as our wave function right here, where we have these linear combinations or superpositions, where the expression for before it gets to the magnetic field here applies only within this range. So we're looking at the width in the z direction, where the plane wave packet has support and the expression after the magnetic field applies only within the triangular overlap region. It's telling us to see figure 1, where the two separating components of the wave coincide. And what he's talking about there is this sort of triangular region after the magnetic field here, where the two beams still overlap. And so that's our overlap region right there. All right, so I'm going to skip ahead here to the red. And so this is just looking at the guiding equation. So no matter its exact location within the wave, the particle will simply drift in the positive y direction with the group velocity of the incident packet. Eventually, of course, the particle will encounter the fields at y equals 0 and pass over into the overlap region to the right of the magnetic field. Here, because the plus and negative components of psi have different dependencies on z, we end up with this right here. So this is our linear combination right here. And so we get these different dependencies on z, which can be understood as a weighted average of the group velocities associated with the two now differently directed components of the wave. So he's saying that it's a weighted average of the group velocities associated with the two now differently directed components of the wave. So it's a weighted average of essentially the group velocities of the upward and the downward part of the wave while we're here in the overlap region. He continues, the family of possible particle trajectories, this looks something like that illustrated in figure 2 for the particular case that the upward spin is a little bit bigger than the downward spin. And so that's this figure here, so figure 2. So we see that there are more lines here going to the upward spin than the downward spin. And so that's saying that the spin is more likely to be upward than downward. And so in the description here, so representative sample of possible particle trajectories through a z-oriented Stern-Gerlach apparatus for the initial wave function with spinor components. So we have the square root of 2 over 3 and the square root of 1 over 3. So we see that the upward has a higher probability than the lower. The particle will move along the incident wave until crossing into the overlap region in this triangular region right here. With the plus and minus components of the wave are beginning to separate. In this region, the particle velocity is the weighted average, given in equation 26, of the group velocities associated with the two separating components of the wave. Depending on its initial lateral position within the incoming wave packet, so depending on where it is in the sort of up and down part of this wave packet here, the particle will either be shunted into the upper or lower fork. Subsequent detection of the particle in the upper lower fork will result in its being identified as the spin up or spin down along z. And so we see how that has to do with that quantum equilibrium hypothesis and the equivariance property, that the particle, before it gets to this magnetic field, has a chance of being in the upper part or the lower part of our wave packet. And in this one, it's saying that it has a greater chance of being in the upper part. And if it's in the upper part, above the critical line, which we can think about over here, but we'll get to that in a minute, then it will be shunted into the upper beam here, where if it's below that, then it will be shunted into the lower beam here. It should be clear, for example, that if the C plus equals 1 and the C minus equals 0, so essentially if it's in a pure spin up state, then while in the overlap region, the particles will just move with the group velocity of the plus component of the wave function, and all incoming particles, no matter their lateral position within the wave, will be shunted into the upward subbeam. And then it's the same thing if we have a pure down spin here. And so let's say that if instead of the square root of 2 over 3 is square root of 1 over 3, if this was exactly 1, then all of the particles will get shunted into the upward trajectory here. So the equivariance property implies that if the position of the particle within the wave is random and psi distributed at t equals 0, it will remain psi squared distributed for all subsequent times. This has the immediate consequence that the probability for the particle to be located downstream of the Stern-Gerlach device in the upper or lower subbeam, and hence is counted as spin up or down, if its position there is detected, is the c squared or the c minus squared here. So that's what I was just saying, that we have the quantum equilibrium hypothesis says that there is a psi squared percent chance of the particle being in some part of this beam in the w or z direction here. So he calls it, the w is the width of our wave packet here. And so that's going to, because of that equivariance property, it's going to remain that way as it moves through time and space here. And so that's why we are going to get it either shunted upward or downward with some probability depending on the wave function prior to getting to the Stern-Gerlach device. It is thus clear that the pilot wave theory reproduces the usual quantum mechanical predictions for the statistics of spin measurements. One of the nice things about the way we have set things up, though, is that this claim can be demonstrated explicitly by considering the critical trajectory, which divides the trajectories emerging into the upper and lower beams. And so that's what's shown here in figure 3, where we can look at this critical trajectory here, where we see that most of the wave packet in the z direction is in the upper part, and only part of it is in the lower part. In fact, 2/3 of it is in the upper part, and 1/3 is in the lower part. And so that's why we will get a 1/3 chance of going to the lower beam and a 2/3 chance of going to the upper beam. One of the nice things he says is that we can look at the critical trajectory. By definition, the critical trajectory arrives just at the vertex on the right of the triangular overlap region behind the magnets. So he's saying that it will meet right here where the two beams are completely separated. So that's the critical trajectory is the one that meets right there where those two things are completely separated. The slope of the critical trajectory is given by the ratio of the z and y components of the velocity in the overlap region. And so it gives this as the slope here, where this is our upward probability and our downward probability subtracted from each other and then added to each other here in the denominator. All right, so moving down here, so like I said, he's just talking about the critical trajectory here, which, like in the previous video, just separates. If the particle is in the upper part, it goes up, and if it's in the lower part, it goes down. And so now he wants to talk about if we have multiple Stern-Gerlach devices put in a line like I talked about at the beginning of the video. But first, he says the pilot wave dynamics for the wave and particle are compatible in the way expressed by the formal equivariance property. The particle trajectories bend just the right amount to yield a final probability distribution over the particle position that is consistent with the usual quantum mechanical predictions, and more importantly, what is seen in experiments. And so, like I've been talking about a lot in the last video and in this video, what he's trying to do in these papers is show that we can get these same predictions from pilot wave theory as we get from the very successful standard quantum mechanics. And so he's sort of saying, summing up here, that this is what he's been able to show. And so now he wants to show that we can think about this with something that is if we have multiple Stern-Gerlach devices put in a line like I talked about before. So he says, so far we have concentrated on the measurement of the z component of the spin using the Stern-Gerlach device whose magnetic field gradient is along the z direction. By simply rotating the device, however, we can also measure the component of the spin along, say, an arbitrary direction n in the xz plane. And so we get this as our n right here, our n component. The whole measurement procedure can be analyzed in exactly the same way we've done before, mutatis mutandis, which just means that we have to make the proper changes to our setup without changing sort of the overall result. So the eigenspinners will now be the eigenvectors of this. So now we aren't looking at sort of pure up and down or left and right angles. So we can look at angles of any degrees here using this as our operator. So this is our Pauli operator in the n direction here. An arbitrary initial wave packet proportional to an initial spinner can be written as a linear combination of these eigenspinners. So again, we have this linear combination here. And the whole analysis of before goes through with z being simply everywhere replaced by n. So it should be immediately clear that the pilot wave theory reproduces the usual quantum statistical predictions for spin measurements, whether it is in the z or some component of spin that is to be measured. Perhaps the theory will fail, however, when we consider the possibility of subsequent and or repeated measurements. The pilot wave theory is, after all, a deterministic hidden variable theory. For a given experimental setup, the outcome of a spin measurement is determined by the initial state of the particle, meaning here the particle plus wave combination. Standard textbook discussions might perhaps suggest that there would be a problem. And so, again, what we're talking about here is we first send our particle beam through a Stern-Gerlach device in the z direction, and then we block out the ones that are spin down and look at just the ones that are spin up. So these are in the pure spin up state. We then send it through a Stern-Gerlach device that's oriented in the x direction, and again, we can get a spin up and spin down for that, and it'll be 50-50 just from the spin up in the z direction. We block out the spin down in the x direction, and then take the ones that are spin up, pure spin up in the x direction, and send those through another Stern-Gerlach device oriented in the z direction. And again, we get 50-50, as if this Stern-Gerlach device in the x direction is completely erasing the pure spin up state in the z direction, and we are now getting a 50-50 chance again in the z direction. The result, of course, is that fully half the particles entering will emerge from the final SGZ, so Stern-Gerlach in the z direction device, as spin down, as I said. The usual interpretation is that the spin along z and spin along x are incompatible properties, corresponding to non-commuting quantum mechanical operators, so the determination of a definite value for the spin along x completely erases the previously definite value for spin along z. Surely a non-quantum deterministic hidden variable theory would not reproduce this paradigmatically quantum result. And so what he means by that is that this result here with the spins going through these multiple Stern-Gerlach devices is sort of held up as kind of a paradigm of the weirdness of quantum mechanics, that we are somehow erasing the pure up state of z by sending it through this x device here. And so if we were thinking about this classically, why would that be getting rid of any upward part of the spin? Why would it then go back to 50-50? But in quantum mechanics, that's exactly what it does. And he's saying that, it seems like if we just think about it intuitively, that a deterministic hidden variable theory couldn't reproduce this paradigmatically quantum result. Then he says, a little thought reveals that yes, the pilot wave theory reproduces this prediction quite trivially. The crucial point is that although the particles entering the x direction Stern-Gerlach device were being guided by waves proportional to this, so this is the spin up in the z direction, the wave guiding those particles, which successfully emerge from the spin up of that first port of the Stern-Gerlach device, or of the x Stern-Gerlach device rather, is proportional to this. So we have 1/2 of going up and 1/2 of going down. And so the plus x and minus x components of the wave get separated by the x Stern-Gerlach device, whereas the particle goes one way or the other. And so he's saying essentially that this is affecting the guiding wave, but the particle still definitely has a deterministic position and velocity given by the guiding equation. And so the guiding equation remains the same. It's that the wave function itself is actually being affected by the magnetic field. And by definition, if the particle ends up in the spin up along x beam downstream of our x Stern-Gerlach device, the component of the wave now surrounding and guiding it is in the spin up along x part. So it is as if the particle's quantum state has collapsed as per the usual quantum mechanical rules, even though in fact no collapse, no violation of the usual Schrodinger evolution of the wave has occurred. The spin up along x part of the wave is still present. It's just over there, or spin down along x rather. Part of the wave is still present. It's just over there, far away from the actual location of the particle. And so he's saying that we're getting this beam splitting, but it's the wave part, it's the guiding wave that's sort of splitting up into the up and down, and then that's just going to carry the particle along one of those based on the equivariance property. And hence the dynamically, so it's far away from the actual location of the particle and hence dynamically irrelevant to the present future of the motion of the particle. This separation of the different spin components of the wave packet, of course, happens in ordinary quantum mechanics as well, but in ordinary quantum mechanics there is nothing like the actual position of the particle in addition to the wave function to warrant talk of the particle actually being up there, i.e. talk of the spin measurement having actually had the outcome spin up. And so additional dynamical postulates are required in standard quantum theory. This is an illustration of the point that although the pilot wave theory adds something to the physical state descriptions, namely the position of the particle, it is not really more, let alone pointlessly more complicated than ordinary quantum mechanics, since this addition allows for the subtraction of the otherwise rather dubious measurement axioms of standard quantum mechanics. What is actually showed by this kind of example is not that one cannot explain the observed statistics of spin measurements with a non-quantum deterministic hidden variable theory, but rather only that the physical state of a particle, known, say, to be spin up along z, must be affected by the measurement, for example, of the spin along x. And so he's saying that the wave function is affected by this by the magnetic field here, and so that's why the particle will sort of get shunted in different directions. Ordinary quantum theory, of course, exhibits this behavior in quantum mechanics. The state of the particle after a measurement is postulated to collapse to the eigenstate of the appropriate operator corresponding to the actually observed outcome. In parentheses, he says, it is worth noting here that the actually observed outcome is yet another additional postulate of the theory. For Bohr, for example, this was realized in some classical macroscopic pointer somewhere whose physical relationship to the particle in question is at best obscure. The point here is that the pilot wave theory also exhibits this behavior. The physical state of, in particular, the wave guiding the particle is different before and after the intermediate Stern-Gerlach in the x direction device. And so again, it's the wave guiding the particle that is different before and after that. But in the pilot wave theory, this difference, the physical influence of the measurement on the properties of the system in question, is a natural and straightforward consequence of the usual, the universal, the exceptionless dynamical laws. And so he's saying that we don't have to bring in some of the baggage of standard quantum mechanics that gives us the measurement problems and things like that when we have our pilot wave theory. And in fact, to me, if you're really committed to the weirdness of quantum mechanics, this almost seems like it's kind of a cheap cop out of it by just saying that the particle isn't actually spinning in some way. We could still talk about the spin of the wave function, whatever that might mean, but the particle isn't actually spinning. It's just sort of getting carried along by this wave, which is affected by the magnetic field here. And so we aren't getting that weirdness of spin of the particle, which in standard quantum mechanics has a sort of intrinsic angular momentum. You'll often hear people say, we call it spin, but nothing's actually spinning. And so it's this weirdness of quantum mechanics thing. But in this case, it's really just the particle is getting carried along by a stream in one direction or the other, where the strength of the stream is being affected by the magnetic field in some way. But yeah, anyway, that is what I wanted to talk about with the spin, with the quantum spin in pilot wave theory. Again, I've been saying this in previous videos. Making these videos can be somewhat time consuming, and so if you get something out of this and you have maybe a few dollars to spare, I do have a Patreon, which is linked to in the description down below. So you can sign up for that if you want to help a poor adjunct professor out here. But anyway, I don't want to harp on that too long. I hope you found this video interesting, and I will see you in the next one.